I'm Alessandra, I'm a neuroscientist. Imagine being a bus driver who must flawlessly combine cues from inside the bus, like the passenger's behavior and needs, with signals from outside the bus, such as traffic conditions. If you can't merge these inputs, your journey quickly becomes chaotic. In a similar way, the brain depends on its communication with the heart to blend internal signals with external cues. This process is called interoception. Interoception is crucial for keeping our body balanced and helping us adapt to the environment. But it's a complex process that involves multiple organs and intricate neural pathways. And this makes it hard to study directly in humans. In neurodevelopmental disorders like autism, this integration is disrupted. And as I told you before, the bus driver journey becomes impossible to manage. As a result, people with autism struggle to merge the signals from within their bodies with the cues they get from the external world. And this leads to significant challenges in daily life. Human genetic studies have identified the gene SHANK3 as a key factor linked to autistic traits. Interestingly, SHANK3 encodes for a scaffolding protein, and it is found both in the neurons, the cells of the brain, and in cardiomyocytes, the cells of the heart. So, it plays a critical role in the brain-to-heart dialogue that underpins interoception. But because of the complexity of these processes in humans and the need to help autistic people, I turn to a mouse model where SHANK3 is deleted. This allows me to study its effect on both the brain and the heart function at a cellular level. At the center of my investigation, there is the posterior insular cortex, a key brain region where internal signals and external cues converge. My primary hypothesis is that within this region, two distinct neuronal populations work together. One, dedicated to processing internal signals, like those from grooming or scratching, and the other specialized in handling external inputs, like those from social interactions. I believe that this dual processing system is key to maintaining the balance necessary for adaptive behavior. For these reasons, I use my mouse model to map how the posterior insular cortex integrates internal signals with external cues. I do so using in vivo imaging techniques to monitor the activity of the neurons, combined with heart recording during behavioral essays. By doing so, I hope to shed a light on the cellular mechanisms behind the disrupted brain and heart communications in autism, and ultimately pave the way for innovative clinical strategies.